Assalamualaikum warahmatullahi taala wabarakatuh. Inshallah, we are going to continue our lecture on chapter 2, entitled as Motion in One Dimension. So, let's begin. Right, so previously we've learned about what is physics in topic 1 or chapter 1, where you are learning actually the physical quantity, the object surrounding you. Knowing the dimension of the object or knowing the character of the object, now you're going to further investigate on the object. You want to learn more about what is happening to the object. Is the object is in motion or not? Okay, that is for chapter 2. So before we go to the motion of the object, right, first thing first, we need to know few things, few basic character or information about position. So position itself, okay, let's recall your memory or prior knowledge on position is actually location of particle or your object, okay, with respect to the chosen reference point. So we need to have a reference point. For example, in this diagram A, you have a car moving from position A to position B, where the position A is 30 meter from the origin. The origin is our reference point. Okay, to the right of the origin is 30 meter, positive 30 meter. This is the initial position of the car. Right, and finally the car reached position of 50 meter, positive means to the right of your reference point or origin. So this is the second position. The third, the fourth, the fifth, and so on. If you refer to the second part here, the car is moving from F to E, let's say, from negative 50 meter to negative 30 meter. Why is it negative? Because it's to the left of your reference point or origin. Okay, so this is about how we define position. Alright, so if we tabulate the information of the motion diagram here to a table, it will look like from the table here we can tabulate the graph position x versus time in second. So this is a graph of the motion for the car, where we have position x versus time t. So if you see here, it's already a curve. Why is it a curve? This is a real motion. Okay, normally or previously you've learned about x versus t, you have a straight line, isn't it? For example, in SPM, you probably going to have, okay, like this. Okay, a graph of x versus t. In real, actually is not a line like this. It must be a curve. Okay, this is a real. Okay, because there is no turning point where you have a sharp point like this. Object cannot turn in sharp point because it has momentum. We'll learn about it later on. Alright. This is about displacement. What's the difference between displacement and position? The displacement, okay, of delta x, normally symbol as delta x, of particle, change in position in a given time interval. That is the displacement. So displacement is change of position. Is change in position. That is a keyword of the displacement. So for vector, okay, it has direction and magnitude. For scalar, only numerical value, no direction. Okay, so for example, in this case, let's say a player, basketball player, okay, for 1 hour of game, okay, the player moving all over, back and forth, approximately, okay, the displacement for the player almost zero, because when it start here, somehow it will, he or she will end here as well. So x final is the same with the x initial. Therefore, delta x equivalent to 0. But we do have value for distance travel by the player. Okay, because it's regards of the direction. Okay, let's say to the front 100 meter, backward 100 meter. Total up in terms of distance already 200 meter. However, for the displacement, since it starts here and it ends here, the displacement is 0. Okay, now we are going to take a look in detail. Okay, again, the graph of the car, the position of the car, x versus time taken, the t. So, if you see here, let's say we take a look on from position A to position B. Okay, delta x displacement of the car will be x at B minus x at A. And if you figure out delta x of the two positions over the time taken, okay, of the x-axis here, okay, so delta x over delta t will give you the meaning of the velocity, right? So if you are considering only 2 points, initial and final points, you are talking about average velocity of the object. So here, this one is actually equivalent to gradient or slope of your graph, right? So it goes the same. If let's say now you're going to consider and now average speed. For average speed, okay, is scalar quantity, remember, is total distance traveled by the object divided by the time taken. Okay, so here, distance traveled divided by time taken. For example, if let's say it takes you 45 seconds to travel 100 meter down long straight hallway, okay, at an airport, okay, as in this figure. Alright, you take you need 45 seconds to travel 100 meter down, okay, a long straight hallway at an airport. At 100 meter, alright, you return back 25 meter along the same hallway to make a return trip. Let's say you forgot something, you want to buy something, okay, so you may have a different information of distance travel and displacement. If you are talking about displacement, you have of 75 meter displacement over the time taken is 55 seconds. So you have average velocity of positive 1.36 meter per second. What does that mean by positive? It means to the right. Okay, if we define the right as positive. However, average speed, okay, must be total distance travel over the time taken. The total distance travel is 100 meter to the right and then turning back for 25 meter. We won't take positive and negative because we're talking about speed. So the only things that we're going to use is magnitude of it. So 100 plus 25 over the time taken. So 55 seconds. So the average speed going to be 2.27 meter per second. That is the difference between speed and velocity in terms of average. Okay, example 2.1. Calculating the average velocity and the speed. Find the displacement, average velocity and average speed of the car in the figure between position A and F. Right. So A to F. From A here to F. Right. So delta X is X final, which is F, negative 53. To be exact amount, you have to refer to the table back. Okay, minus XA, 30 meter. So you have delta X between A to F is negative 83 meter. Right. Now velocity. So from here, substitute x final minus x initial, okay, which is negative 83 just now, over the time taken. So you will get the V average, which is amount of it is negative 1.7 meter per second. What does that mean by negative? It's to the left. Right, now average speed, okay, instead of using change in position or displacement, for speed we are going to use distance traveled. Right, so distance traveled will be 127 over the time taken 50. Okay, so now the value is 2.54 meter per second. Next one will be instantaneous velocity and speed. So this is a figure of our previous example, a car moving from position A to position F. Okay, and then here is another approach, okay, where we have a bigger picture of this part, okay, A to B here. So we make it bigger here. Okay, so from A to B, okay, the distance traveled quite big and time taken also quite big for 10 seconds. And if we want to have a even smaller time interval, okay, we can have another approach where we're going to take blue line here become smaller. Okay, the blue line between position A and B approaches the green tangent line as point B is moved closer to the point A. So if let's say throughout this, okay, taken time is 10 seconds. If let's say we want to have a particular time, okay, at this position, okay, let's say 2 seconds, let's say at that particular time we want to know what is velocity of the car, right? So how are we going to do? Okay, we are going to take tangent to the position, okay, and then figure out the slope of the tangent line. Okay, based on this concept, okay, become smaller in time. So finally for one single position, it's represented by the green line. The green line is the tangent at that position. Okay, so this is in terms of technical. So in terms of mathematics, what does that mean by tangent line there? Okay, to have the velocity whenever the time interval is very small, okay, that particular velocity is named or called as instantaneous velocity. What does that mean by instantaneous? Whenever the time is very small, okay, very particular time. So how to do that? Okay, what are we doing when we're taking the tangent? We are actually doing the limit. Okay, in calculus, this limit called derivative of x with respect to the t. Okay, derivative of x with respect to the t, written as dx over dt. Okay, so it's written as dx over dt. Right, example 2.3, a particle move along x-axis. Its position varies with time according to the expression of x equivalent to negative 40 plus 2t squared, where x is in meters and t is in second. The position time graph for this motion is shown in figure. Right, because the position of the particle is given by a mathematical function, the motion of the particle is known at all time. Notice that the particle move in the negative x direction for the first second of motion is momentarily at rest at the moment t equivalent to 1 second, and move in the positive x direction at t equivalent to more than t bigger than 1 second, more than 1 second. Alright. A, the question. Determine the displacement of the particle in the time interval between 0 and 1 second and 1 to 3 seconds. Alright, how to do this one? Displacement between 0 to 1 second means that from A to B. Okay, so delta x from A to B is equivalent to x final, which is the B, minus x initial, which is the A, right? Equivalent to -4, okay, based on the equation given, times 1 second, final time is 1 second, plus 2 times 1 squared minus -4 times 0 plus 2 times 0 squared. Okay, so you'll get -2 meter. For delta x from 1 to 3 second, it's from B to D, equivalent to x final is xd minus x initial is xb. Okay, so in terms of value, make use the formula given, substitute the information, which is t, according to the t. -4 times t final is 3 second plus 2 times 3 second squared minus -4 times with 1 second plus 2 times 1 second squared. You'll get positive 8 meter. Alright. Part B. Calculate the average velocity during these 2 time intervals. Average velocity. So how to do this one? V average, okay, is equivalent to V in terms of x direction, average from A to B, equivalent to delta x AB over the time taken, which is the one that we calculated just now, meter over 1 second. So you will get -2 meter per second. For second part, okay, average from B to D, equivalent to delta x B to D over the time taken, which equivalent to the one that we calculated just now, 8 meter, positive 8 meter, divided by 2 seconds. Then you're going to have positive 4. Okay. C. Find the instantaneous velocity of the particle at 2.5 seconds. Okay. So, what are we going to do? We are going to calculate the slope of the tangent for the green line, because, okay, because 2.5 seconds, let's say in the middle here, okay, will be this point. Okay, for this point, for one particular point, can we calculate a slope for one particular point? Actually cannot, because slope or gradient is defined as gradient or slope, okay, symbol is m, is defined as delta x, how much of the change interval, okay, of the displacement over the time taken, right? So this is actually the velocity, okay, in terms of x direction when the t is 2.5 seconds. So you have to take the tangent line for only one position. The approach is you're going to take tangent line at that particular position, so which is slope. Okay, so based on this, okay, your Vx is equivalent to 10 meter minus negative 4 meter over 3.8 second minus 1.5 second, which give you positive 6 meter per second. So where did I get 3.8, 1.5 here? Is the reading for the tangent line, the reading of this one. Okay, must be accordingly lah. Okay, so 3.8 for this one, 3.8 here, 1.5. And in terms of delta x is negative 4 here, negative 4 information of this, and positive 10 information of this. So it's taking this point and this point, okay, to calculate the slope, okay, because it's touching or tangent to 0.5 second of time here. Example 2.4, modeling a runner as a particle. Okay, kinesiologist is studying the biomechanics of the human body. Okay, kinesiology is the study of the movement of the human body. Notice that the connection to the word of kinematics. She determines the velocity of an experimental subject while he runs along a straight line at a constant rate. So the scientist starts the stopwatch. Okay, at the moment the runner passes a given point and stops it after the runner has passed another 20 meter away. The time interval indicated on the stopwatch is 4.0 seconds. The question. What is the runner's velocity? Velocity. In terms of x-axis, the runner is running straight away in terms of x, right? So it's delta x over the time taken. Equivalent to, when we talk about delta, it must be final minus initial position, okay, over the time taken. It's 20 meter minus 0 over 4.0 second. There we go. We have 5.0 meter per second is the runner's velocity. B. If the runner continues his motion after the stopwatch is stopped, okay, what is his position after 10 seconds have passed? So we are looking for final position, x final, okay, minus x initial, okay, equivalent to v naught plus v final t. Okay, so x final is the one that we want to know, equivalent to v naught, and x naught or x initial start from 0, right? Start from rest. Okay, this is reference position. Okay, then we have v final in terms of x times with a t. Then we have 5 times with 10 seconds. Then you're going to have 50 meter. Average acceleration. So still talking about the car just now. Okay, if let's say whenever the car is in motion, it moves from position A to position B, however, with different velocity. At point A, another value. At point B, another value of V. Okay, the slope of the green line is the instantaneous acceleration of the car at point B. Okay, but the blue line here, okay, connecting point A and B, okay, is the average acceleration of the car during the time interval. Why? because now you have graph of v versus t. Because acceleration is defined as rate of change of velocity. Okay, similar approach to the instantaneous velocity. For instantaneous acceleration means that we want to know the value of the acceleration of the car at very particular time, very short time interval. At this particular t only, what is the a of the object? So, or the car. Okay, for one position, again, what you're going to do, you're going to do the tangent line. If you're talking about average, it must consider 2 points of position from A to B. So you're going to have gradient between these 2 points. That is average. When you have tangent line and figure out gradient for the green line here, that is instantaneous acceleration. So, in terms of proper definition for the instantaneous acceleration is actually limit, okay, of the delta x to the respect of the delta t, or we can, okay, put it as derivative of velocity with respect to the time, okay, or also known as rate of change for the acceleration. That is the instantaneous acceleration. So this one is the definition of instantaneous acceleration. Acceleration versus time graph. Okay, what we have here, okay, v versus t. This is information of velocity versus time. Now, this information going to be converted into A versus T. Okay, the figure illustrates how acceleration time graph, okay, related to the velocity time graph. Acceleration at any time, okay, is actually the slope of the velocity time graph. Velocity versus time graph, the slope of this will be the acceleration value, right? Acceleration reach maximum at time ta here, okay. The slope of the velocity, because the slope is positive, okay, increase, isn't it? Alright, then it's become maximum value. Right, acceleration goes to 0 at t equivalent to tb. Here, becomes 0. Why is it so? Because velocity maximum, just now, velocity maximum, okay, where the slope of the vt graph equivalent to 0. So, in simple, okay, every time you want to know what is the acceleration to be plotted at this time, figure out the slope. Okay, figure out the slope of v versus t graph. Right. Then, acceleration negative. Where? Here. At t equivalent to tc. Okay. When the velocity decreasing in positive x direction, it means that it reach most negative value at tc. Okay, decreasing. So the slope is negative, that is why it's negative value. Okay, so actually you will get okay, for TA here, tangent line. Okay, so you reach one value, of course starting from 0. At this point, tangent line here 0, so 0 value. Okay, when you have tangent line here, it's no slope, right? So that is why it's 0 here. Okay, this one AX maximum. Okay, here is 0. And then here, negative slope, right? That is why it's negative value, negative AX. When you have this, okay, so in terms of motion, you're going to put it not a straight line. In previous primary school, if you have this kind of AX, versus t, and you have point like this, and finally 0 again, you are going to put it straight line, isn't it? Or we can finish it. Actually, this is approximately only. The correct one is this one. This is a real situation. It's not a straight line like this. It's a curve. Okay? So, we can conclude that if you have V versus T graph and you want to convert this graph, information from this graph into A versus T, what you're going to do, figure out the slope at any position that you want to take out the data. Now we're going to proceed to acceleration. Acceleration is defined as change of rate of change of velocity. So in terms of calculus, okay, it is proper to write down dv over dt. Okay, so the vx, okay, is equivalent to dx over dt, not to forget about that. Okay, so acceleration also can be written in terms of x, okay, where we call it second derivative of particles' position with respect to the time. So second derivative of the position to the respect of time. Alright, okay, next one. Conceptual example, graphical relationship between x, vx, and ax. Okay, so what you have here is position of an object moving along the x-axis varies with time, as in figure. The graph of velocity versus time and the acceleration versus time for the object. So here you have x versus t. How to have another two graph, how to get information from x versus t graph here and make another two graph. So take a look on this. Okay, we are going to have v versus t. Between t equivalent to 0 up to t equivalent to ta, the slope of the x versus t graph, okay, increases uniformly. So figure out the slope. So the velocity increase linearly as shown in this part. Right. Between ta to tb, from here to here, okay, the slope of the xt graph is constant value. So if constant value, the slope is constant, means that the velocity going to be a constant, a flat, okay, in terms of graph, a constant value. Now from tb to tb to tt, from tb to td, the slope is decreases. So the value of the velocity in vt versus x, okay, for this part, decreases as well. At td, the slope of the xt graph is 0. At this point, the slope of the graph is 0, because if you take a tangent to this, it's a flat line, so it's 0. So okay, the velocity is 0 at that instant. So if we have to take a look on td, the velocity is 0 because the slope is 0. Alright, between td to te, okay, the slope of the xt graph here, okay, there is a slope, therefore the velocity are negative, and because the slope is also negative, and it decreases uniformly in this interval. So from td to te, it decreases, okay, and then from te to tf, here te to tf, okay, the slope of the xt graph is still negative, and tf is goes to 0. Okay, it goes to the same position, right, same position. So means that, okay, for the velocity, okay, at tf, for the graph of x versus t, okay, it becomes 0 value. Finally, after the TF, okay, the slope of the xt graph is 0 because it's flat line. Next one. Now you have the A. To get the A graph here, you have to figure out the slope of the V versus T. Okay, for example, a constant slope, right? That is why the A is 1 value. Okay, no slope, right? That is why the A all of a sudden drop to 0. Because no slope here. There is slope, but negative. That is why negative throughout, one value, one slope, one single slope, and it's negative slope. That is why your A is dropped to the negative value like this. Right, and here, increase positive slope. Okay, that is why your A all of a sudden being like this, one value between TE to TF. Okay, and there is no slope, 0 again. Example 2.6. Average and instantaneous acceleration in example. The velocity of a particle moving along the x-axis varies according to the expression of Vx equivalent to 40 minus 5t squared, where Vx is in meter per second and t is in seconds. Okay, so this is a graph. Okay, the question. Find the average acceleration in the time interval between 0 to 2 seconds. Make use of the formula given or information or expression given just now. V at in terms of x-axis at point A equivalent to 40 minus 5t, t which t at A lah for sure, squared, equivalent to 40 minus 50 times with 0 squared, which give you positive 40 meter per second. Right, V velocity along x-axis at point B is equivalent to 40 minus 5t at point B squared, equivalent to 40 minus 5, sorry, this one is 5 actually, okay, times t, the t at B is 2 seconds, which give you positive 20 meter per second. Okay, to have A average in terms of x-axis average, it must be delta V over delta T. So which V? V along X at a final position, B minus V along X at initial position A over the time taken. Okay, so 20 minus 40 over the time taken between 2 and 0 seconds. So you will get your answer negative 10 meter per second squared. For part B, okay, determine the acceleration at t equivalent to 2 seconds. For particularly 2 seconds, for particle or very small time interval, okay, very short time, okay, we call it instantaneous acceleration. Okay, to figure out instantaneous acceleration, you're going to take a tangent line in terms of technical way. In terms of calculation, by using calculus, okay, you're going to calculate V final along x-axis, V final equivalent to 40. Make use of the formula or expression given just now, 5t plus delta t squared. Right, so if you open up, okay, this parenthesis, you're going to have 40 minus 5t squared, right, plus negative 10 t delta t minus 5 delta t squared. Right, So delta V along X must be Vx final minus Vx initial, negative 10 T delta T minus 5 delta T squared. Okay, because what is our X final? The whole bulk of this, isn't it? What is our X initial? X initial is this one. X initial is this one. Okay, so if you minus that, okay, let me put it here. Okay, Vx initial is 40 minus 5t squared. So if the whole bulk of this formula minus this one, then you are left with this only. Okay, so now back to our calculation. We have done the formula for delta V. Now now A along X, okay, is limit delta V along X to the respect of time when your time is very small or approaching 0. So limit of negative 10t minus 5 delta t, okay, is equivalent to negative 10t. Right. So if you want to have a particularly at 2 seconds, so the A is negative 10 times with the T, which is 2 seconds, then it's going to give you negative 20 meter per second squared. Okay, why is it adding delta T here? Because later on, isn't it? Because we know that the initial velocity is this one, right? And then if we want to find final velocity, of course it has extra additional time. Okay, that is why we put the T now plus delta T. For motion diagram here, if you refer to figure A, here B and C, you have different information. For figure A, the car is moved at constant velocity, how we know, and 0 acceleration, because the arrow representing the vector of the V, okay, is written here at the same length and the same direction at the almost the same constant time interval. So the velocity is constant or uniform. So when the velocity is constant, there is no acceleration, because acceleration is defined as delta V over delta T, right? So if there is V but the V is constant, so there is no delta V. That is why in figure A, the acceleration is 0. No arrow representing the acceleration. For figure B, this car has a constant acceleration in the direction of its velocity, because the velocity is increasing uniformly. That is why the A is uniform or constant, right? Then the C, this car has a constant acceleration, but in opposite to the direction of the car or velocity. How to know from motion diagram? If you refer here, from one position to another position is getting shorter, okay, and the amount of the arrow, the length of the arrow representing the vector of the V also shorter and shorter. It means that the car is now slowing down or decelerate. That is the meaning of opposite in its direction.